Lecture today is on Coulomb's law and superposition, kind of our first time digging into the real content here. All right, and we know what Coulomb's law does, or hopefully you already know what Coulomb's law does. It gives the force between two charges. And we can write it in a few different forms, but the form we're going to look at today is this. The electric force, vector force, can I have everybody mute yourself? So I just want to make sure it stays on my paper. It stays on the screen. So the electric force is, I'm going to use, instead of the Coulomb's constant, 1 over 4 pi epsilon naught. And we'll see how that relates to the Coulomb constant in a second, times the first charge, times the second charge, divided by the distance between those two charges squared. And that gives us the magnitude, right, the number of the force, but we also want to make sure we have the right direction, and that's why we put in here the r hat unit vector. And any vector, well, every vector is going to have either an arrow over it like this, which indicates that it's a vector. Some vectors you'll see have this hat symbol over them, and that means that it's a unit vector, that the vector has just length 1. So really the only important thing about these vectors is the direction that they point. And yeah.
The r hat's just direction, right? It's nothing like, it's not a variable, it's just the direction of r.
Yeah, it's the...
Okay. Word.
Okay. 1 second here. I'm gonna see if I can make it just stay focused on my paper here, even when it okay. Because I want you to be able to jump in with questions without everybody losing sight of what they're copying down. So that should work. Thanks. Okay, so just for the record, then the epsilon naught, that's 8.85 times 10 to the minus 12 coulombs squared per Newton meter squared. And that's called the permittivity of free space. It's related to the speed of light, or really the speed of light is related to this. And it just basically sets the fundamental strength of the electric force compared to other forces. Usually you don't want to have to bother calculating 1 divided by 4 pi epsilon naught. It's easier just to often use another constant, K. That's Coulomb's constant, which we define, right? And the three lines here look like an equal sign with an extra line. That's equals, but it's even kind of stronger than equals because we're saying K is defined to be this. It's 1 over 4 pi epsilon naught. And I think you've already used it and know that it's to 3 sig figs, 8.99 times 10 to the 9th. And the units are Newton meters squared over Coulomb squared for Coulomb's constant. Right, so you might be wondering, it's weird that we have these two constants, but really sometimes one is easier to use than the other. And you'll kind of see when we go along when that happens. You can, it's usually going to be your choice which one you want to use. Probably you'll find K is more often useful than epsilon naught, but you want to be aware of both of them and what they mean. And I just want to write down the definition again of r hat. That's the unit vector. And we'll learn more about unit vectors tomorrow and unit vector notation. And it points from the first charge to the second charge. So being specific about it. So it points from Q1 to Q2. Right, so that's what, if you have Q1 and Q2 drawn on your paper, you can draw an arrow pointing from Q1, Q2, and then you know exactly what way r hat is pointing. We want to be as unambiguous as possible with our vectors. We want to always know exactly what direction they're pointing. And we also will see later on that r hat, if we want to be able to write it in terms of the x and y coordinate axes, we'll be able to do that. We're not going to look at this much today, but we'll come back to it tomorrow. R hat's just going to equal the cosine of the angular coordinate times I hat, so the x direction, plus the sine of the angle times j hat, so that's the y direction. And we're going to get used to kind of converting back and forth between polar coordinates, r and theta, and rectangular coordinates, x and y. And this equation here will help us do just that. At this point, I want to, especially if you took a mechanics last year, you should note the similarity. Oops. Of Coulomb's law to Newton's universal gravitation law. And if you remember, the force of gravity between any two masses is Newton's big gravitational constant times the first mass times the second mass divided by the square of the distance between them times r hat, so the direction from the first mass to the second mass. All right, that's almost exactly the same equation. The only difference is instead of charge, we have mass in gravity. And instead of the Coulomb's constant 1 over 4 pi epsilon naught, which is big, right, times 10 to the 9 power, that's a big constant, that's 9 billion. We have Newton's big G constant. Does anybody remember the value of that?
Big G?
Big G.
Oh, I know little g, bro. I don't know big G.
Okay. Big G is really small. It's about times 10 to the minus 11 power, right? So it's a tiny, tiny fraction compared to so that's how we can tell that the force of gravity in general is much, 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 much weaker than the electric force, because Newton's big G there is much, 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 much smaller than Coulomb's constant. But since those equations are so similar, the problems with electricity, electrostatics really, are often similar. The same equation means they're going to behave in pretty much the same way. And this is why we can think of an electron orbiting a nucleus kind of like a planet orbits a star. at least until you get to quantum mechanics. Right? But it's the same equation, so you kind of get the same behavior. So next we'll see the superposition principle. But are there any questions on the Coulomb's law that we've seen so far? All right. So next, the superposition principle. All right. Coulomb's law told us how to find the charge on or the force on a charge from one other charge. Superposition principle is going to tell us how to find the force on a charge from more than one other charge. And it's as kind of simple as you'd think, really. You just kind of add them up. You just have to add them like vectors. So the force on a charge from more than one other point charge, and we're going to do some examples as well, so you'll see, is equal to the vector sum of the force from each individual charge. And let's see, I think I'll go on to the next page to put our examples. We're just going to look at two examples of the superposition principle, and that'll be it for today. So I'll give you a moment to finish copying anything you need or looking at anything you need from this page. And we'll look at two examples of the superposition principle, how to add those together like a vector sum. Okay with this? Okay. So we're going to do two examples. So example one. We're going to put two charges. So here's our coordinate system. We're going to put a minus q, a charge of minus q up here. We're going to put a charge of plus q, a positive charge down here. And then we're going to put another charge over here at the origin. We're going to call that one positive lowercase q. And we're going to want to find out what the electric force on the charge at the origin is. So to write that out, we have 2 point charges. I'm sorry, both of these, we're going to make both of these negative. Two-point charges that are minus q, capital Q, are at, we'll say the coordinates are 0 and 3 meters for charge A. We'll call that point A. And 4 meters, 0 for that second charge B. So what is the electric force on a test charge? I'm calling it a test charge because that's the charge that we're kind of putting near these other charges to find the force on it, which is positive, and we'll call it lowercase q at the origin. Okay, so we've got two negative charges here and here. Let me label this as RA, this vector, and this vector is RB. And really the vector points from this charge to the charge we're looking at. So this first vector is a downwards pointing arrow, the RA, and this RB is a leftwards pointing arrow. So let me ask you guys, what direction, if we look at this first charge, the minus Q that's over here, what direction is that going to be exerting a force on the test charge? So the test charge feels a
down
direction.
down
Downward.
what? Yeah, that.
Agree, disagree. We've got a negative charge here and a positive charge there, right? Do negative charges and positive charges, are they going to repel or attract?
Fact. God damn it, I'm an idiot.
No.
What? I'm so confused. God damn it.
It's all right. Well, so answer that question. Do unlike charges, right? This is a negative, that's a positive.
Oh, it's like charges attract, right? And
Yeah.
Yeah. Okay. So yeah, I was right the first time. It's down.
Okay, so if they're going to be attracted, right? What direction would the force on this test charge be if it's attracted to
Up.
charge? Right, it's going to be pulled upwards, right? Does everybody see that? We have a positive charge here. There's a negative charge up there. It's going to be attracted to the negative charge, so it's going to feel an upwards pull from that charge. What direction is it going to feel a pull from the charge that's over here?
The left. Like it's gonna go left or try to go left.
This is also a negative charge,
Yeah.
and this is a positive charge. So these are unlike charges, so they're going to be attracted. So what direction is this going to be pulled if it's attracted to this charge?
To the right.
Right.
To the right. All right, so just looking at it qualitatively, this charge is going to feel an upwards pull towards this one and a rightwards pull towards this one. So when we add those like a vector, it's probably going to be at some kind of angle up this way. All right, it takes a while to kind of get used to and get comfortable to which direction these are going to feel a force. But that's fine. You'll get it. So now we actually use Coulomb's law and we use the superposition principle, and we'll get an expression for the force on that test charge. So let's look at the first one. So if we just look at this charge up here first, we can say the electric force for this one is going to be, well, 1 over 4 pi epsilon naught times Q1 and Q2, right? So that's going to be our big negative Q. Oops, there's a line on my desk that's making it hard to write under this paper. So we have negative Q times Q, right? Those are the two charges, divided by the distance between them, squared. Right, so that's this distance squared. And we can tell this distance is just 3 meters, right? And the r hat, the direction from this charge to that one, that's just straight down, right? If we look at the not talking about the direction of the force, just the direction of the r vector, that's minus j hat, j hat being the direction along the y-axis. Have most of you used the I hat, j hat terminology before?
Yeah.
In in mechanics last year, or in calc as well?
Mechanics.
Okay.
Just in mechanics.
Wait, if it's negative j hat, is it the same thing as like the whole expression being negative and then j hat, or?
Well, yeah, I mean, you can multiply a negative, and multiplication is associative, right? So you can put that negative anywhere. So yeah, it's the same as if, and we're going to do that. We're going to see this negative here is going to cancel out with that negative there.
Oh, okay. Yeah, that makes sense.
So this is basically the force from the force on our test charge from this top one here. There's another charge, right? This one as well. So we just need to add that one too. So plus the force from the second one there is also 1 over 4 pi epsilon naught. We're just right back to Coulomb's equation, Coulomb's law, times this one is also, we have a negative q as one charge and a positive little q as the other charge. The distance between those two is RB squared. Well, the distance is RB, and we need to square that. And the direction is, the r hat here is from our negative q to our test charge is to the left, so along the negative x-axis. So that's a minus I hat for the direction of this one.
Wait, why?
Because r hat we divide. So if I go back to the last page, right? R hat is the unit vector that points from Q1 to Q2. And
Yeah.
on the first charge is this one, and the second charge is this one.
Okay, cool. I get it now.
Okay, so that's basically almost our expression. We just need to plug in because we do know what RA and RB is, right? We know RA equals 3 meters, right? That's the distance from here to here. And RB equals 4 meters, right? That's the distance from here to here. And I'm being careful to, since I'm just talking about the distance, I don't have the arrow over my RA and RB here, right? These are just numbers, just magnitudes. So if I plug in now and kind of factor out, right? In both terms, I have so look, I can look at this. I notice that all of my negative signs cancel out, right? I've got 2 negative signs in each term, so I can ignore my negative signs. And both terms have a lowercase q and a capital Q over 4 pi epsilon naught. And then the first one, RA is 3 squared, right? So that's 9 in the denominator. So I have 1 over 9 j hat from this term. And then this term, right, I've already taken out the 4 pi epsilon naught, the 2 q's, canceled out the minus signs. RB is 4 meters, so 4 squared is 16 in the denominator, so 1/16, and I have the I hat left over. All right, so I just did standard algebra here to simplify this expression down to this expression here. So that would finally be the electric force on our test charge. Right, and we wouldn't plug in any numbers. This would be, and you're going to find that a lot in this class, that your answer is just going to be an equation, an expression like this. And this is going a little longer than I had hoped to take the lecture to take, but I do want to do one more example for today. But are there any questions so far? The next problems that you're going to be assigned are pretty similar to these. And if you can kind of keep track of, if you're good about keeping track of which directions your R hats are, it makes it much easier, because then in the end, you just have to do the algebra and you can cancel out your minus signs if you need to and all that.
I have a question. So the 1 over 4 pi e, isn't that just Coulomb's constant?
Yeah, it's the same as Coulomb's constant. Yeah. So
Can't we just like put the letter for it, or do we need to write the equation every time?
you can use if you want to use k instead of 1 over 4 pi epsilon naught. That's fine. And in most situations, you should probably do that. I know that, or I think that the equation sheet for the AP test has the. I should go back and check. I think it has it as 1 over 4 pi epsilon naught. And I'm going to get used to going back and forth and using both of them.
It doesn't ever get changed in the equation. So, do we need to worry about knowing the 1 over that specific equation?
You don't. So on your equation sheet on the AP test, it's going to have both of them listed for you with a value.
I see.
So you'll be able to look up either one.
Thank you.
So one more example, and we'll stop for today. Example 2. So in this one, we'll put, let's see, we'll go, there's going to be a charge of plus q here. We'll put a charge of minus q here. And then our test charge will be plus little q again, and that'll be over here. So we want to find the electric force. On the charge, or on the test charge. And I'm just using a different letter, a lowercase q for this one, just so that we can remember that's the test charge and not the charges that are providing the force. This charge will be exerting a force on the other two as well, but we don't really care what that force is. Placed at x equals 2 meters. From a charge plus q at the origin. That's the first one there. And minus q at x equals 1 meter. Okay, so this first charge is at the origin. This next, so all these distances are 1 meter. Okay. So again, we're going to use the superposition principle, right? So if we're looking at this charge, first we will find out what the force on it from the charge all the way to the left is, and we'll add the force on it from this charge here. Okay? So my electric force is going to be, and again, I'm going to use 1 over 4 pi epsilon naught. If you'd rather use k, that's fine. So I have capital Q, which is positive from the first one, and lowercase q, which is also positive. Those are my Q1 and Q2. And divided by the distance between them squared. Well, what's the distance from the charge all the way over to the left to my test charge?
2 meters.
2 meters, right? So if I square that, I would get 4 meters squared. All right, I'm gonna just do that out. I think everybody can do 2 squared. And what direction? What's the direction from? Not talking about the force yet, just the direction from the plus q here to my test charge.
Positive I hat.
Yeah, that's in the positive I hat direction, right? This arrow from the vector from this charge to my test charge is just to the right. So positive I hat, that's right. So this is what I would get as my force from the first charge. Then I add the force from the second charge. And that's 1 over 4 pi epsilon naught. This one is a negative capital Q, so I got to make sure I put that in as the charge, times my lowercase q. And what's the distance between the negative q and the test charge?
1 meter.
That's a 1 meter distance, right? So if I square 1 meter, 1 times 1 is still 1. So I have 1 meter squared. And again, remember, I'm just going back and using this equation, right, for Coulomb's law, and plugging in exactly everything, right? I wrote it down 1 over 4 pi epsilon naught exactly. I plugged in what we had for the first charge exactly, what we had for the second charge exactly. The distance between them, right? This isn't a vector, it's just the distance squared. And then I need the r hat vector again, right? So the vector from this negative q to this positive q, what direction do I have to go to get there?
Sure.
Go ahead.
Okay. So for the second, the thing that we added, that is it a negative I hat for that, or?
It's
Okay.
still just when we put in the r direction, we don't worry about the force or the sign of the charges. Just what's the direction from this charge to that charge.
Okay.
So it's not going to be negative I hat, right? What will it be?
Just I hat.
Just
Okay.
again, right? It's the same as the other one. Even though the charges are different signs, we have to go directly to the right to get from this charge to our test charge. We also have to go directly to the right, to get from this charge to our test charge. So that's why both of these are going to have I hats. The fact that they're different sign charges, we see just comes in here, right? This one's a negative Q, and that one doesn't have a negative sign. Okay, so that's basically the electric force. We just need to simplify this down a little bit, right? But we've put everything in. And if we had more than 2 charges, right? If there were 3 charges or 6 charges, we would have an equation here with 3 terms or with 6 terms. I don't think I'm going to give you any problem that has six in it, but that's just the way the superposition principle works, right? You have to add them together like vectors. So let's see what this simplifies down to, and then we'll be done for the day. We can factor out the 1 over 4 pi epsilon naught and the capital Q and the lowercase q. And also the I hat, right? We have an I hat in both terms. And then we have basically 1 over 4 meters squared minus 1 over 1 meter squared. And let me get rid of my let me get rid of the units here for now. So really this is 1/4 minus 1. And what's 1/4 minus 1?
Negative 3/4.
Negative 3. Right, negative 3/4. Right, so what we have then is Q over 4 pi epsilon naught times lowercase q times negative 3/4 times I hat. And we can simplify that one, just one last small amount, and get the electric force. So we've got a 4 down here and a 4 down there. So it's going to be minus 3/16 QQ over epsilon naught I hat. And that can be, it doesn't matter if you write that as one fraction. All right, but that's as simplified as we can get this. And I didn't leave the units of meters in because my units are, then I would kind of only have some of the units in my answer and not others, because some of our units are contained in epsilon naught and in Q. So when you're giving your answer as a formula, as an equation, you usually don't need to have units in there. This is a vector. So it probably seems like a lot, but we kind of went through it very slow and in detail. Once you kind of have the hang of these, plugging in your Q's and your vectors for the for Coulomb's law isn't too bad. Are there any